So what we have now, and this is very important, I have fast variables and I have slow variables. That is the next real step of sophistication in the theory that I need to make. So again, I have energy levels. So in principle, this looks just like the models I had before. Nothing changed, except there's two sets of energy levels. There are the slow energy levels, which are now going to describe the quantum theory I'm interested in, which is here. This is a logarithmic scale for the energy levels. So when I go high up, I get energy levels hundreds of times far higher than here. And there are very many of those. They're all also equally separated, but the separation between these energy levels is much, much bigger than these. Now imagine this theory, and now say this is real quantum mechanics. Suppose our world looks like this. What happens if I apply thermodynamics? Thermodynamics hasn't been mentioned yet. But in thermodynamics, you can say that if the thing is in somewhat near a thermal equilibrium, then I'll get equipartition. The states with high energy are suppressed by small Boltzmann factors. The Boltzmann factors for all these states are so small that at first approximation I can neglect them all. Then I only get the slow energy spectra, and the slow energy spectra will obey my rules of being possible to combine them to make this thing deterministic. My claim is now the following: the world as we know it has its energy spectrum more or less arranged like this. There are very fast fluctuating variables, which for that reason have very wide separated energy levels, which are all not occupied because of thermodynamics. Their Boltzmann factors are too small. You can also compare the situation with with the standard model, which contains particles that are too heavy for us to see. In the standard model, there are perhaps Higgs particles or other particles that we have not yet understood because the LHC has not been able to reach those particles. Those particles will all be sitting in the ground state, not moving at all, only making slight changes in the model. So now I'm going to say, yes, this is going to be my theory, but there will be interactions between these states and this one. And now the interactions are of the kinds you already had discussed using the questions. In the question, one of the questions was, can you hop over from these levels to these levels? Now I'm saying in this picture, yes, I will introduce the possibility that every now and then a particle hops from here to here or hops from here to here. I'll just add that as a possible law in the game. However, those events where a particle interacts with particles from the background are rare. I'm postulating now that yes, every now and then the particle in this world interacts with the particle in this world, but the interactions occur rarely, only every now and then. And this happens if, for instance, compare now the treatment of the standard model, but the standard model contains the particles we know, but also contains the particles we don't know yet. That's why it works so badly today, because probably there are many particles that we have not yet been able to open up to see what they are like, because they haven't been produced. Their fields have not yet been excited. So now I have many very short circles in my theory. Those short circles are going around so fast that the energy levels are very far away from each other due to thermodynamics, due to the fact that these high energy levels could not be reached by hand in any possible way. I don't see those fast fluctuating variables. So real quantum mechanics comes about when you have all these levels, but you missed them all because you couldn't see them. But now I can imagine those energy levels to be there. Then I get a model that looks much, much better like quantum mechanics that you know of than before. You get that these very many, very high energy states form a background of highly fluctuating states, so highly fluctuating that they look like white noise. Now I'm in a situation that I can add particles that may be unstable, that can decay with an exponential decay law, and so on. So this is the main rule is now that, yes, you have fast variables, but we cannot follow them. We cannot measure them. Therefore, we encounter the real quantum mechanical nature of our world because we are missing out on looking at those fast vibrating particles. And then by doing that, you get a new and interesting situation. Now the theory looks much more like quantum mechanics. I'm going a bit faster because I wanted to go into the consequences of such a theory. And my claim is that well, that what happens, it now happens, it looks very much like the things that happen in a cellular automaton in practice. A cellular automaton contains particles that move very slowly around, and they're very fast linking things that make these slow moving objects behave like behaving at random. So now you see I have a classical model with random behavior put in, but the behavior is random because the universe is so large. So these classical states in the high energy mode can vibrate, but in a very short time, they go through all possible states they can go through. So they look actually like a multiverse and all these things people talk about. But now I've introduced them in a way that looks much more like deterministic. So the universe is deterministic, but only if you are able to follow exactly everything that happens in these particles. Let me see. Well, how to go about
question? Can I?
Yeah.
So, is this line of thought? I mean, so the resulting equation is different from Fokker-Planck type equation. So so in classical mechanics, if we introduce some stochastic noise, whatever, then eventually we will have some Fokker-Planck some equation. So this kind of thing. So starting from Newtonian equation, introducing some stochasticity, can you derive Schrödinger equation instead of a Fokker-Planck equation? Or so yeah.
Absolutely, a good question. Yes, my claim is yes, because basically this model is like the first models are introduced. They are very simple. They are deterministic, but only deterministic if I take this fluctuating background into account. I take all the states the fluctuating background can be in, then it becomes deterministic. But imagine that's so much work to think of every single fluctuating object at every point in space and time. It's hopeless to follow all that behavior. So the Fokker-Planck equation will work very, very well. But now I have set it up in such a way that I can see how to turn this into a deterministic theory. In principle, all the states are deterministic. So every single fast fluctuating variable can be in L states. L's are the enzymes that I had before, but now there are very, very many of them. And now I can ask, how do I set up a theory, and how can I reproduce the Schrödinger equation that I want? How can I reproduce the Hamiltonian that I want? And what I'll do now is I'll show a method to produce the Hamiltonian out of a deterministic theory. The big question will then be, is that the right deterministic theory I chose? That is a very difficult question, and I cannot answer, but I can answer the question, how can I make a model that looks like the model I want to produce? For that, I introduced the Pauli matrices, sigma 1, sigma 2, and sigma 3. They are 2x2 matrices, and they will be acting whenever a particle makes a decision. Do I go this direction? Do I go that direction? And now I have to say, well, this time there'll be a new ingredient in the theory saying the particle can go in this direction or it can go in that direction. But that depends on where the fast fluctuating variables are. Well, they're going so fast, I can't follow them. I can't tell you where they are. So because of that, I can only give you a quantum amplitude. But if I could follow these fast-moving variables very fast, then I could write down exactly the quantum amplitude for the particle to go either this direction or that direction, because it's now deterministic. So it's a Fokker-Planck equation, but a deterministic Fokker-Planck equation, which only generates random numbers because our universe is so big. If the universe were as tiny as a few Planck lengths, it wouldn't be random anymore. It would be completely deterministic. But no, our universe is very, very large. All these random oscillators interact with each other, not very, very intensely, but sufficiently to make it hopelessly non-periodic and stochastic looking. So I introduced the Pauli matrices, which can be in two states. One state is that the particle went this way, the other state is the particle goes that way. And to introduce a flip operation. So the unitary operator that tells you whether the particle goes this or that way is an operator which gives you a flip. And that flip is that one of these Pauli matrices will serve as a flip operator. This actually is a Pauli matrix that tells you which of the two states are you in. Are you in the flipping state or in the non-flipping state? These two say, I make the flip, but I can make it in two ways. So that is, I still can control the phase that I put in. The phase has no physical effect. So strictly speaking, sigma 1 and sigma 2 are not distinguishable from each other. But in practice, they are, when you do the mathematics, they are different. And they have the same mathematical properties that the Pauli matrices normally have. But now I want to write a Hamiltonian that generates that flip. And Hamiltonian is relatively easy to get. You have to take these Pauli matrices, but multiply them with a constant alpha, which is always 1/2 pi. It's not 1/4 pi, not 1/3 pi. It must be 1/2 pi. Why? Well, e to the power 1/2 pi times I times these matrices gives you this matrix again. If it were not 1/2 pi, but something else, then it would become a superposition. All 4 entities of the matrix would be different from 0. That would be a quantum superposition. So now, postulating that I have a deterministic theory that is mimicking from quantum mechanics is the same as postulating that these coefficients are exactly 1/2 pi and nothing else. It's nice, it's not nice what I get out of this. If it's 1/2 pi, it's deterministic, but it isn't really quantum mechanics. So now you can say that this theory will be quantum mechanics only if it makes these alphas 1/2 pi, but not in the other case. But I want to mimic real quantum mechanics. In real quantum mechanics, I often have the Pauli matrix with very different coefficients. So I want these alphas to be different from 0. Actually, I want them to be very, very tiny. If they're very tiny, you have another mathematical machine at your disposal that's better than the Schrödinger equation because it gives you faster the probabilities. And I'll tell you that in a moment. I have a machine as follows. I can take my flip operator, but now I say the flip only takes place if all the fast-moving particles are in certain positions. That's what I said before about the unstable particle. So the unstable particle reacts only if the fast variables in the immediate surroundings take certain values. Then I have to multiply the Hamiltonian with the Kronecker delta function. That doesn't change anything. It doesn't make these alphas smaller or bigger. They're still 1/2 pi, all of them, but now they're multiplied with delta functions. Those delta functions are 0 most of the time, but every now and then a delta pops up, and then the particle makes a flip. So classically, this is completely deterministic. But now I have an operator which I can say is very small. But in what way is it small? Well, its expectation value is very small. Because if this fluctuating background is stochastically moving, then at every single moment, the probability of these x's being realized is very, very small. So the vacuum expectation value of this interaction Hamiltonian is very small. It has the same one as before, with the coefficient alpha being 1/2 pi. This is the Pauli matrix. But now there's a 1/L1 times L2 also in expression. This is the expectation that the fluctuating variables have the right value. So you see, I'm combining quantum mechanics with stochastic physics. This you could call stochastic physics, but I'm using quantum notation to describe it. But what I describe gives me something that looks very much like the standard model, because I have an interaction Hamiltonian, just like the standard model, and it is very small because of these L's, just like the standard model, and I have a way to solve it mathematically, just like the standard model. What I can do is I can do a perturbation expansion, but making a sequence of terms, writing down Feynman diagrams for all these terms that tells you this very small coefficient comes in once, comes in twice, comes in 3 times. I'm doing the perturbation expansion. I'm terminating the perturbation expansion whenever the next term is so small that it doesn't make any difference anymore. That is exactly what you do in quantum field theory. So I'm claiming now we have to do the same thing as in quantum field theory, but now I know what the interaction Hamiltonian is. The interaction Hamiltonian is a Pauli matrix times a coefficient 1/2 pi, which I should not forget, times a number which is very small if the hidden fast moving variables can move in very, very many different positions. Only in one position, this term pops up. So this term on the average is very small, and the method is accurate because I may make this assumption that this background is fluctuating more or less randomly. So now the notion of random fluctuations does come in, and now the theory I get out looks much more like quantum mechanics.